Hello everyone, welcome to CE4390 Chapter 5, Compacting and Finishing. In this video, you will learn the first section of Chapter 5, which is about the compacting work. Here are the learning objectives. First, understand when to use each of the various compaction methods. Second, ability to estimate compaction production. Section 1. Compaction of soil and rock. First, what is compaction? Compaction is the process of increasing the density of a soil by mechanically forcing the soil particles closer together, thereby expelling air from the void spaces in the soil. Compaction is like squeezing out the air. What are the results of poor compaction? Cracks, leaks, in basements and pools. Slab cracks. Pipe leakage or breaks. Foundation erosion. Erosion gullies under abutments. Utility trench settling. Section C. Let's learn some terminologies. The figure down here shows the cross-section for two different types of pavement. The one on the left is called asphalt concrete, or AC. It is also known as flexible pavement structure. The one on the right is called Portland cement concrete, or PCC, which is commonly known as rigid pavement. A pavement structure is typically composed of many layers, each of which is made of a certain type of material. As you can see in the figure, AC and PCC are composed of the same types of layers, except for the top surface layer. Now, let's learn the terminologies of those pavement layers. The bottom layer is called subgrade. It is typically made of native soil. Laid above subgrade is the subbase course. It is a layer of a selected type of material, such as recycled concrete, manufactured aggregate, and crushed rock. The base course is one that is constructed directly above the subbase course. It consists of construction crushed aggregate, such as stone or gravel. The pavement is the surface course, laid on top of the base course. This layer can be asphalt or Portland cement concrete. If asphalt is used, the pavement is known as AC pavement. If you use PC concrete, it is referred as PPC. Soil is placed and compacted in layers, also known as lifts. A compacted lift is about 8 to 12 inches. Remember that lift thickness can either refer to material as spread or as compacted. The degree of compaction that may be achieved in a particular soil depends upon the following factors: the soil's physical and chemical properties, such as gradation. Gradation refers to the size of the particles. The figure on the left shows poorly graded soil, while the one on the right shows well-graded soil. The soil's moisture content also has a great impact on the compaction. Moisture content indicates how much water contained in soil. The compaction methods, as well as the amount of effort, will also greatly influence the degree of compaction. Compactive effort is the total load that you apply on the compacted area. Compaction methods can refer to the type of machine, whether it is a big rolling compactor or small vibrating machine. Finally, The compaction is highly determined by the lift thickness. Too thick may lead in a low compaction result. Section F, optimum moisture content. To identify the relationship between the moisture content of a soil and its density, we typically use two tests. Test 1, Standard Proctor Test. Test 2, Modified Proctor Test. This test is developed for use when high design loads are involved, such as airport runways. You can see Table 5.1 for details characteristics of the test. You are also encouraged to review geotechnical courses for this topic. Compared with the standard test, the modified test has more than 4 times the compactive effort of the standard one. This is Figure 5.1 in your textbook. This curve highlighted in yellow here is resulted from the standard test. It shows the relationship between water content and dry unit weight. This curve is from the modified Proctor test. As you can see, given the same water content, test 2 leads to a higher dry density. In addition, the optimal moisture content from the modified test is lower than the standard. Since different tests give you different dry density and optimal water content, compaction specifications must clearly specify what test to be used. They typically express the minimum required density to be achieved as a percentage of the standard or modified Proctor density. This is a moisture density relationship curve for a certain type of soil. From this chart, the optimum moisture content is 16.6%, which can result in a maximum dry unit weight of 109.6 pounds per cubic feet. If the spec requires 95% of the max density, the desired density is equal 95% of 109.6 or 104 pounds per cubic feet. Using this chart, you can identify the required range of the moisture content. It should be from 12% to 21%. If the soil has too much water or the moisture content greater than 21%, you need to dry the wet soil by using scarifier on a grater or a tractor with discs or additive solutions such as lime. If the soil is too dry, you can use water trucks to wet the soil. This shows the use of disking to dry the soil. Here, a water truck is used to wet a compacted area. Water trucks can be small with 7,000 gallons. For large areas, you may want to use bigger trucks, such as Caterpillar 341. It can carry up to 42,000 gallons. Normally, it is good practice to adjust water content to 2% above the optimum value, but this adjustment depends on wind, temperature, and soil type. Section 2, Methods for applying compactive effort. The impact method compacts soils by dropping load on the compacted surface. Another method uses the pressure of static weight. The load is laid on top of the surface. The third method of compaction is the use of vibration or shaking. Finally, kneading is also a common way to create compactive effort. The compaction method selected depends upon the type of soil to be compacted. This table here is from Multiquip. For example, vibration is good for sand, and the recommended lift thickness is around 10 inches. Section 3, Types of Compaction Equipment. You can see some common types of compaction equipment in Figure 5.3 of your textbook. This is a snapshot of Figure 5.3. It lists common types of compaction equipment. The top left is a smooth steel wheel roller. The top right is a self-propelled vibrating roller. We can also use multi-red pneumatic rollers or heavy pneumatic rollers, as shown in the bottom. Here are some other types of roller. The one on the top left is a self-propelled tamping foot roller. The top right is a self-propelled segmented steel wheel roller. The bottom left is a toed sheep's foot roller. And the one in the bottom right corner here, this is a grid roller. Again, compactors are typically classified based on the type of roller. This picture here shows a sheep's foot compact. It creates compaction by high-pressure static load. Caterpillar says, this roller can compact up to 8-inch lifts. This is a picture of sheep's foot roller. This picture shows another type of roller. It is called pad foot compactor. It compacts by either the static load from its weight or combined with vibration. This is one example of pad foot compactor. Some machine adds vibration to make additional compactive effort. This is tamping foot roller. This figure shows the difference between a tamping foot and a pad foot. This roller compacts soil by the static weight and kneading. It is suitable for compacting all fine-grained soils. It compacts soil from the bottom up. In other words, soil in the bottom of a lift will be compacted before soil in the surface. It can be used concurrently, following pneumatic or smooth drum, to compact upper 2 inches to 3 inches. This is a smooth drum roller. Some machine has single drum, some others have double drums. This uses both static and vibratory load to make compaction. It is suitable for cohesionless soils, such as the materials used for subgrades, bases, asphalt bases, and wearing courses. This single drum roller can compact a lift thickness of up to 9 inches. Double drum rollers are usually do shallow lifts, less than 4 inches. This one compacts soil from the top to bottom. The surface is compacted before the bottom layers. This figure shows one example of single smooth drum, integrated with the vibration system. This is one example of double drum vibratory compactor. This is a pneumatic tired compactor. It creates compaction by static load and kneading action. This machine is suitable for most granular soils and not effective for fine-grained clays. This figure shows the arrangement of tires. It has 4 front tires and 5 rear tires. This is a plan view of the tire. As you can see, the front and rear tires are well arranged, so that their paths will cover a maximum compacted area. This is called grid or mesh compactors. This is another view of mesh compactors. This type of compactor makes compaction by static load and impact load. It is best for clean gravels and sands. One unique advantage of this roller is it can operate at relatively high speeds. Caterpillar or other manufacturers can provide you with some guidance on what type of compactor to use for different types of material. This is figure 510 in your textbook. This figure summarizes when each type of roller should be used. For example, steel wheel is recommended for rock, but it is not recommended for sand. This is the compaction guidelines made by Caterpillar. It is in page 2215. From this figure, vibratory compactors are best for rock or sand, but is not recommended for cohesive materials such as clay. Other methods of compaction are also used. This is one example of impact compactors. The roller has a triangular shape. It is like dropping a load when it is rolling. The impact rollers may have a hexagon shape. Heavy pneumatic compactors are another type of roller. It is capable of compacting soils to depths up to 18 inches. Dynamic compaction is also commonly used. It can densify to depths of about 30 feet using 30-ton weights and 100-foot drop heights. Let's watch the following video about how dynamic compaction works. Another common type of compactor is vibratory plate. It is suitable for granular soils and asphalt. It is typically used for small areas. We also use rammer a lot. It is best for use in confined spaces. It is typically used for small work. Another type of roller is trench roller. It is typically small and commonly used for compacting trenches. It is flexible and can make turns easily. It works like a robot. As we discussed previously in other chapters, hydraulic hose can be used as a compactor. This is a wheel compactor attached on the boom of the excavator. A plate compactor can also be attached to the excavator. This type creates compaction mainly by vibration. Section D, Intelligent Compaction. This is new technology for compaction work. This part of the lesson is only for CE639 students. The graduate students are encouraged to read more details about intelligent compaction, which can be found in the link on the top. Section 3, Estimating Compaction Production. For estimating compaction production, we use equation 5.1 as shown here. Production is measured in compacted cubic yards per hour. In this equation, N is the number of roller passes required. W is the compacted width per roller pass, measured in feet. S is the average roller speed, in miles per hour. L is the compacted lift thickness, in inches. E is the job efficiency. 16.3 is the factor for converting the results to cubic yards. The typical operating speeds for various types of compactors are given in Table 5.3 in your textbook. For example, the speed of heavy pneumatic compactors is ranging from 3 to 5 miles per hour. Now, let's do an example on how to estimate compaction production. Scrapers will deliver to the project 600 lcy per hour of fill material. It is dry clay. A self-propelled tamping foot roller will be used to compact the fill. The rolling width is 84 inches. Test strip compaction information indicates that 9 passes at 3 miles per hour are required to obtain the required density. The fill material will be placed in 8-inch compacted lifts. You are required to determine the number of rollers required to support the scraper operation. To estimate production, you need to use equation 5.1 as discussed earlier. Let's see what are given. We got the rolling width of 84 inches. The number of passes and the speed are given as 9 passes and 3 miles per hour respectively. The compacted lift's thickness is 8 inches. Let's apply the equation 5.1. In this equation, W is the width for roller, is 84 inches, or 7 feet. S is the speed, which is 3 miles per hour. L refers to the compacted lift thickness. It is given as 8 inches. N is the number of passes. It is 9 passes. E is the efficiency. It is not given. So let's assume the efficiency of 83%. Now, we got all the information we need. By calculating this, you get the production of 253 compacted cubic yards per hour per compactor. Going back to the problem statement, remember that the total amount of material is given in loose cubic yards, but what we got for production is compacted cubic yards. So you need to convert from LCY to CCY. Also, you are required to determine the number of rollers required. Note that, until field tests are performed, We do not know the exact conversion from LCY to CCY. Let's review what we got. 600 LCY per hour of material coming in to fill. 253 CCY per hour of material compacted per compactor. Compacted lift thickness is 8 inches. Remember that this is the thickness after being compacted. We don't know the thickness of loose soil before being compacted. If it is given, we can easily convert LCY to CCY. If assume loose lift thickness of 10 inches, the conversion factor would be 8 inches divided by 10 inches, or 0.8, as the conversion factor from loose to compacted. To calculate the total compacted volume, you multiply 600 LCY by the conversion factor of 0.8. So we got 480 compacted cubic yards. If we assume loose lift thickness of 11 inches, the conversion factor would be 0.73, then we got 438 CCY. If we assume loose lift thickness is 12 inches, the conversion factor would be 0.67, then we got 402 CCY. To determine the number of compactors, you divide the total amount of compacted soil by the production. If assuming 10-inch loose lift, it is 480 divided by 253, or 1.9 compactors. You repeat that process for 11 and 12-inch loose lift. You got 1.7 and 1.6 compactors respectively. Therefore, we should use 2 compactors which can satisfy all 3 scenarios. Section D. Use Caterpillar Handbook to calculate production. We will no longer cover this Caterpillar method. You are not responsible for the material from this point on in these Chapter 5.1 notes. This is the end of this video. Please complete all the homework problems in this chapter. Goodbye for now, and see you next time.